Boleh kita mulai, Prof.
Boleh, insya Allah.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Pagi ini. Kemudian ada appreciation yang tinggi dari our departemen ke Prof. Karena berkenan untuk uh, lecture dua sesi weeks, this Friday and Faculty of Engineering. Terima kasih ke Bapak Ibu dalam lecture ini. Ada 30 partisipan yang siap hadir. Kemudian mereka dari our student sendiri, especially diambil subjek uh, electrical machine. Kemudian beberapa pensyarah dari mungkin di Jawa Timur dan di seluruh Indonesia, kumpulan namanya Forte, Forum Teknik Elektro Indonesia, eh, Cawangan Jawa Timur dan nasional.
Pak Wijono, lainnya macam lagging lah, Pak. Saya nggak bisa dengar dengan jelas. Adakah ya, yang lain juga begitu?
Pak Wi, internetnya bermasalah sepertinya.
Oh, internetnya ya.
Atau laptopnya yang bermasalah, Pak Wi.
Tadi sudah cek sound.
Oke, oke. Sekarang bisa.
Nah, sekarang bisa. Ada ada perbaikan di network internet kita.
Oke, oke. Apa, insya Allah. Masih lagi lagging.
Izinkan saya share ke sedikit ya sedikit tentang oke sambil tengok gambar ini. Prof. Eran lahir tahun 1978, 31 Agustus. Ini hari kemerdekaannya.
Ya, benar.
Kemerdekaan Malaysia ini. Kemudian Prof. Erwan adalah senior lecturer di University Tun Sen On Malaysia sejak 2015 ya, Bro. 2015. Kemudian beliau mengajar ke beberapa subjek, electric engineering, generation, distribution, and so on. And then supervision beberapa student PhD, ada 12 di sini, master ada 15, all in power system ya, in power, power engineering.
Ya, ini electrical engineering.
Electrical engineering, oke.
Pak, saya rasa perlu tengok
Kemudian,
semua Pak, panjang nih Pak. Saya kalau tengok CV saya tu.
ya, ya, kita scan saja ya.
Ah,
Kemudian riset muslim.
Rasanya internet Bapak masih lagi lah.
Motor elektro gitu ya. Ke sekitar.
Atau saya bisa langsung saja.
Oke, oke, ke sila Prof dimulai. Terima kasih.
Baik, baik, baik. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Uh,
Waalaikumsalam warahmatullahi wabarakatuh.
please give me a few minutes so that I can upload the document. Okay, all right. So can you all see the screen?
Ya,
Okay, we can see that.
Okay, all right. Uh, okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to
waalaikumsalam.
the host of the from Universitas Brawijaya, Prof. I think Dr. Wijono, or we can simply call Pak Wi. And also the audience. I think most of the audience is come from the same university, and also students and lecturers. I would like to express my fruitful of thank you for your invitation in giving me sharing my experience. I'm not sure. Is it okay for me to speak in full English or combination of Malay Indo language?
It's okay, speaking in English, Prof.
Okay.
No problem, Prof.
So then I will continue my lecture today in full English, inshallah. So basically, what I would like to share this morning is about the flag switching machine. The flag switching machine is actually a new type of machine that has been evolved not recently, maybe about 15 to 20 years back. But only recently, people and researcher who did design and optimization in electrical machine, focusing on the flag switching machine. So today I will share part of the fundamental and some operating principle in how the flag switching machine operates. So before I start my presentation, I would like to how to say a bit intro about my background. So actually, I was born in Johor, Batu Pahat, Malaysia on 31st August, is the independent day of Malaysia. So I graduated from University Malaya in 2001. And then I also uh, finished my master in electrical in Kuito in 2004. Actually, I joined UTHM also in 2004 after I just finished my master. Actually, Kuito is a college university before it upgrade to university in 2007. Then I went to Japan, Nagoya Institute of Technology in 2012. Sweet. And then also in 2016, I got my professional engineer so that we can use the title IR in front of my name. And also, I just completed the diploma on Imam Professional in 2022 in detention. This is just actually the part of my, I can say, the part-time extra education, because we can see the whole life I finished on engineering. So I just want to proceed in some Islamic background study, inshallah. So, what is my goal today? My goal today is basically to share with you all the structure, basically the structure, and then the magnetic circuit concept, and also the working principle of flag switching machine, which highlighting their advantages and also the application as well. So as we can see from the animation here, we can see that this is some type of flag switching machine. that generally, before I go through the detail on the operating principle, this animation shows that the rotor itself is nothing but a salient pole rotor without any flux sources, no windings, no polar magnet, and the flux is rotating around the stator to the rotor that makes the rotor rotates. So the detail I will explain later. And then the contents of my presentation, I have only 5 main topics: introduction, fundamental of electromagnetics. This is very basic electromagnetic fundamental that is very, I think, is very useful for especially students and for us to recall how the electromagnetics generation can make the energy conversion that finally make the rotor or generator rotates. And then I will share some of the electrical machine available, and then I will go to the fruit of the lecture, that is the flux switching machine, and then I will summarize and make a conclusion. So as an introduction, it's nothing but I will share all this topic, okay, about the global electric motor capacity, electric motor application, classification, and also AC synchronous motor itself. So as an introduction, we know that the global electric motor capacity, the motor industry in the world has been used from the few decades, and we can see that electric motors are the core components of anything working with electricity. And from the research, it is found that the electric motor consume approximately half of the power used around the world. So from this chart, we can see that this chart is showing that the utilization of equipment, global electricity consumption. So we can see that electric motor itself, or electric machine, utilize about 46% of the electricity. When we go deeper, we can see that out of 46%, most of the electricity has been used in the industrial motor. We can see that 65% available in the industry, heavy industry, and also in part of SME groups. And 20% of the electric motor used in the EV, 10% only in residential, in our home, our house, and commercial, and the rest for transportation and IT stuff. So what happened is actually here we can say that the motor itself, we can see is very important in our life. Even we cannot avoid the operating, the application of electrical machine or motors in our daily life. Okay, this is some of the many example. Okay, I will not go through detail on this. I just want to highlight a few items such as the appliances in our home, such as vacuum cleaners, cooler, fan, and our laptop itself. And also for transportation, including the EV or car. In car itself, we have more than 50 electric motor, including small scale motors such as the DC motor and so on. And also for the robotics, printers, wind turbine, and so on. So because of that, we can also categorize the electric machine classification. So basically, when we study electrical machine, so what we have to understand is nothing but 2 items. That is how the electricity come from. So first, electrical machine can be divided into DC machine, because first electrical supply can become from DC itself, such as from the battery or from the inverter. And second is we have AC machine, that is can be plugged in directly to the power outlet, either our house or office and so on. So I will not focus on this DC machine. So maybe if you are interested, we can have another slot on this machine itself. Today I will focus only on the AC machine parts. An AC machine can consist of transformers, okay, single phase, 3-phase, as well as auto transformers, and also AC generator, okay, and also AC motors. So in AC motor, we have 2 types. In general, we have 2 types. That is induction motor itself, that has been used generally in many applications in our home, in industry, and so on. And also the new type of the synchronous motor that I will go through in detail later. So we can see here about 50% of the world electricity is used to run induction motor. Okay, so induction motor is very important in our life. We cannot avoid that, even though we didn't feel that what to say, the movement of the rotor itself. but it is very, very useful. It's very, very important in our life. So thanks for the people, to the researcher, for the previous researcher who did and found the induction motor itself. So now we go on the AC synchronous motor. So basically in AC synchronous motor, we can categorize into 4 types. First is the synchronous motor that have a permanent magnet in the rotor itself. Okay. So in the rotor itself, because rotor is basically the rotating part, so they can add the permanent magnet either in the surface of the rotor itself. So they call is surface PM or SPMSM. There is surface permanent magnet synchronous motor. In short, we call SPMSM. Second, they can also install the permanent magnet itself inside the rotor. So we call it interior permanent magnet. In short, we call it IPMSM. And also, the second categories of the synchronous motor can be from the DC excited rotor field, which means that I can say that all the stator condition for this synchronous motor are almost similar. The difference is only based on the rotor itself. So the first thing, they have a PM in rotor, permanent magnet with the constant magnetic flux. The second type, they have a DC excited rotor field, which means they have an external source from the DC supply. So that when the DC supply is coming to the rotor, so the rotor will be energized with the flux line and flux distribution and can react with the armature flux so that the rotor can be rotated. So 2 types of DC rotor, either using a slip ring, okay, slip ring as well as the brush and the commutator itself. And also there is a brushless excitation without a slip ring. The third type of motor can be based on the reluctance. There is no rotor field, no permanent magnet. The rotor is just a hollow rotor itself. They can be divided into synchronous reluctance and also switch reluctance. Another principle of the synchronous motor can be the hysteresis, and also the newest one, that is the flux switching motor, that can be categorized depends on the flux sources that come from magnet, EM, FE, field excitation, and also hybrid, that is a combination of magnet, field excitation, and also field excitation. Okay, before I go through deep on the process or the operating principle, I would like to recall, I would like to give a bit sharing on the electromagnetic fundamentals. Okay, this is very fundamental for us and for the student who take the course of electrical machine. Okay, 3 things that we will discuss is about the magnetic field that come from the magnet, and then magnetic field come from current carrying wire, as well as the energy conversion when both magnetic field are attract or repel each other. So first of all, in this world, permanent magnet or magnetic flux can be achieved from the permanent magnet itself. So magnetic field from the permanent magnet is a constant. It produces steady magnetic field without electrical input. So this is very basic magnet that we can use it, and we can play it around. Some of the easy how to say application that we are used to have is that when we go travel, so basically we will buy a fridge magnet as a souvenir, so that we can give the souvenir to our relative, and they will put in the fridge, in the refrigerator. So because of the constant or steady magnetic field, so it doesn't generate electromagnetic energy, but it provides the magnetic field used in energy conversion. Later, we can use it in the motor or the generators. And the source of the magnetic from magnets basically come from the magnetic material itself, either from the ferrite or the neodymium ferrum boron. This is an example of the very high flux density of the magnet itself. So in permanent magnet, this is very normal, very fundamental that there is 2 pole. There is north pole and the south pole, and always the field magnetic line flows from the north to the south pole, from the upper part and also from the lower part, to make a complete cycle. The second magnetic field that we can generate is from a current carrying wire. Okay, as we can see from the fundamental, when we have a current, we have a wire itself. The blue one is the wire. So when the current flow to the up of the screen direction, so based on the right hand grip rule, okay, right hand grip rule. So this is our thumb. So and then the rest of the finger is the direction of the magnetic field. So which means that magnetic field is generated when there is a current flow in the wire. So the concept is when the electric current flows through a conductor coil, it produces a magnetic field around it. Example, in an electromagnet, current through a wire wound around an iron core generates magnetic flux. The source can be from electrical energy, either from battery, generator, or other power supply. Then the current carrying wire can be formed or wound into the solenoid condition. So we can see that more magnetic flux will be generated when we form a loop circle of the solenoid. So for example, from this figure, we can see that the current flow is from the positive terminal of the battery. So when the current flow in this direction, okay, in the upper part of the slide, so we can see that the magnetic field generated that is from our palm. Okay, so when we look in the simple figure, we can say that current flow from bottom to the upper part of the solenoid. Okay, then the generation of the field magnetics will come from the left side. That is, we can consider as a knot, and then it will make a one cycle that is come to the south part. Why is important for us to understand the concept of magnetic field? It is actually nothing but from the magnetic field itself, we can have an energy conversion. Energy can be produced when we play around with the magnetic field itself. For example, in our daily life, if we take two magnets, okay, magnet one, we have a south pole, and the magnet two, we have south pole here. So when the south pole is close together, what we'll have is that the pole will be repelled, okay, it will go far away because of the same polarity of the magnetic field itself. And then if we have a magnet with a different pole, south and north, so it will be, sorry, so it will be attacked together. So this is actually the basic principle of how the motor operation happen, because when we have a two flux sources, okay, either one of them is north or south, or both have a same pole, same polarity of the magnetic pole. So the process of repelling and attracting will be way around there, and then it will convert to the movement. I think we have experienced this in our daily life. We can see that if we put two magnets together, okay, it will try to attach when the unlike pole are when the unlike pole is north and south are attached together. But if the difference pole, for example, north pole together, so it will be repelled, it will go far away. So this is actually the basic movement for the student of who are taking the subject of electrical machine to understand the principle of how the electric motor rotate. So the idea is that if you want to make the rotor to rotate, okay, if you want to make the motor to run, first thing we have to produce two flux sources in that motor. So either the flux source come from the stator or the flux source come from the rotor itself. So the idea is that the motor itself must have two flux source. When there is two flux source, then energy will be converted from the magnetic field to the mechanical energy. That is the movement or the rotating of the rotor will be happen. The same goes when we look at the detail on the energy conversion from a magnet itself. So from this figure, we can see that there is a rotor coil here, okay, and there is a permanent magnet. So when the rotor coil aligns with the stator permanent magnet, so unlike pole attract, okay, and the rotor move forward, rotor will move to the clockwise direction, motor moves to the clockwise direction. So when it continues to rotate, the like pole repel. So when it repel, so the continuous of the rotation is the going on, and then we can see that the rotation of the rotor itself will go to the clockwise direction. Okay, from the basic of the fundamental on how the energy conversion happen. So Alhamdulillah, very good researcher from the previous decades have designed and developed many type of electrical motor. So in here, I will focus on brush DC motor, brushless DC motor, induction motor, field excitation synchronous motor, as well as permanent synchronous motor. So first, we look at the brush DC motor. Brush DC motor is actually a very simple motor. Okay, in general motor, we have the stator itself. Okay, in the motor itself, and then we have the rotor, shaft, frame, stator winding, and so on. But what is the key point here is first, in the how to say, in the stator itself, they consist of permanent magnet. Okay, permanent magnet here, south and north is the permanent magnet inside the armature itself. So permanent magnet is considered as the one flux source. Okay, so but if you want to rotate the rotor, if you want to make the movement happen, okay, we want to change the energy from magnetic field to the movement of the machine or the rotor itself. We must produce two flux source. Okay, the first flux source is constant, that is from the permanent magnet. So the second flux source can become from the external DC that is supplied directly to the rotor itself. So from this figure, we can see that there is a carbon brush, okay, and also the commutator, and also the supply directly to the rotor itself. Okay, this is the DC supply. This supply from the rotor itself will go through the carbon brush and commutator. And then when there is a two flux there, there is first flux from the stator magnet, and second flux that is come from the rotor, from the DC coil outside to the rotor. So when there is two flux there, so a movement will happen and the rotor will start to rotate. Okay, this brush DC motor is basically work on the principle of Fleming left-hand rule. Okay, we can try to play around with our left hand. You can see that the thumb is the force, or we can say this is F. And we have also our point finger. Okay, this is the magnetic field B. And also we have the electric current here, our middle finger. You can put it as I. So this FBI is the basic principle of the Fleming left-hand rule, that how the rotation will be happen, the force will be happen, and the rotor will start to rotate. So when we look at the this condition, okay, we have electric supply passes through externally through commutator. Okay, current flow upward direction. Okay, and current will flow to the brush and the commutator, and then it will go to the coil. Okay, this part is the stator. Stator itself has a constant permanent magnet that is come from north to the south like this. Okay, so the magnetic field direction B is like this. Okay, so direction constant for magnet is like this, and then we have a current flow in the coil in this direction. So when we use the Fleming left-hand rule, so we can say that the force will be generated in the upward direction. The force will be generated in the upward direction, and we can say that the rotor will be rotated in the clockwise direction. So this is a very simple fundamental operation of the brush DC motor. Then to avoid the use of DC external brush and also the commutator, So researchers have developed a brushless DC motor. Okay, brushless motor is nothing but they are using a special sensor that we call the Hall effect sensor. That is to tell the controller where is the location of the rotor. In a very simple way, for example, if we have a sensor here, we put a sensor here, okay? The sensor will sense the flux flow to the sensor itself. So then what they will do is they will give input to the from sensor to the electronic controller. So a controller is nothing but the brain. So what they use here is to give a command to the to the supply, which supply is need to be energized. So it will execute in a 6-step commutation sequence, and it uses PWM to regulate speed and torque. If you look at the animation, you can see at one time only two armature coil is energized. For example, left and right, up and left, and so on. So this is actually the work that comes from the electronic controller or the microcontroller unit itself. And then when you see there is stator winding, there's the muscle that create the rotating magnetic field based on the controller command. And we have the rotor that is from the magnet that follows the rotating magnetic field, converting electrical energy into mechanical rotation. So the basic principle is still there. To make the rotation happen, there must be two flux sources. Okay, the first flux source comes from the rotor itself. Okay, you can see from the animation, the rotor itself is considered a permanent magnet, and the second flux source is come from the armature, itself. All right. So the detail of the BLDC or brushless DC motor is nothing but we have a sensor, we have a Hall effect sensor. This figure, we can say we have 3 Hall effect sensor. Okay, for example, this sensor, okay, it will say that I'm now receiving a negative flux from the magnet nearby me. Okay, this is the south polarity of the magnet. So this sensor will say that negative flux is come from this side. So when there is a negative flux come from this part, so the sensor will give the input to the microcontroller, okay, and then the microcontroller unit will give it to the interface circuit to make a decision which circuit is need to be energized. So under this condition, we can see that when the sensor sense the magnetic flux in this condition, so the MCU will tell the interface circuit, okay, now I want you to energize U plus, okay, and also U minus, for example. So what does it mean there? In this condition, U plus will provide the north polarity of the magnetic field direction, while U minus will generate the south polarity of the magnet itself. So when there are two flux, okay, first flux is from the rotor, second flux is come from the coil. So the interaction will be happen, and at this condition, when there is a north and north polarity between this, so it will repel, and when south and north polarity of the condition, so it will attract together. So this will make the rotor try to rotate either in clockwise or counterclockwise condition. Okay, still the idea of the rotating rotor is nothing but we must have two flux sources. Okay, and then the other motor that I have discussed previously is about the induction motor. And induction motor is the most widely used motor in the world. As I mentioned previously, 50% of the equipment in our life using induction motor itself. Because it simply use the AC supply. Okay, the key advantage is that because it uses normal AC supply from the power outlet from our home, okay, from office and from the industry. So it consists of normal, okay, stator coils. Okay, there's a stator itself. and also cast iron frame, and basically it has a squirrel cage rotor. So as I mentioned before, the basic principle to make the rotor rotate is that we must have a two flux source. Okay, so from the induction motor, we can see that the first flux source is come from the external AC supply. For example, we have the AC supply. We can directly connect to the wiring box here that will be supplied to the stator. So the first flux come from the stator, and then we have a squirrel cage rotor itself. Okay, the second flux will be generated in the rotor flux. That is the squirrel cage rotor will produce the rotomatic flux density. So when there is a two different flux there, so the action or the energy conversion will be happen. Okay, and why people choose to develop induction motor? First, because of their simple and rough design. Most of the induction motor is actually use squirrel cage rotor. Basically, there are two types of rotor for induction motor, either squirrel cage or one rotor. So most of them are using squirrel cage rotor because they don't have any brushes or commutator, so that the operational life will be longer and also low maintenance cost. So in terms of the cost effectiveness also, they are cheaper and easier to manufacture than other type of motor. And the most important is that it runs on common AC power supply. Okay, we can plug directly into standard wall outlet. Okay, for example, we have a washing machine in our home, we have a ceiling fan, we have a stand fan. Okay, we have the blender machine and so on. So that can be directly plugged into our socket outlet. Another thing is that the reliability is can able to withstand tough industrial condition with minimal breakdowns, and also that it has a versatile application that can be used in household appliances to industrial machinery. Okay, induction motor a bit because it is very important and because it has been used from a few decades ago, so it's very important for us to understand why they call induction motor. So induction motor is called induction motor because the rotor, okay, the rotor voltage is induced in the rotor winding instead of physically connected by wires. Okay. In case of previous DC motor, we can see that we need to energize the rotor itself, or we energize the stator itself by giving the external DC supply. But in the case of the induction motor, okay, the rotor don't have the rotor that are using a squirrel cage. They don't have any physical winding attached to the rotor itself. But the rotor can produce the induced voltage. Okay, the rotor will produce the voltage that we call induced voltage. Later, I will show how the rotor generate the induced voltage. So there are two types of rotor: the squirrel cage and one rotor. So most of them are using the squirrel cage rotor. Okay, if you have a broken fan or broken blender or washing machine in your home, you can try to operate and open the induction motor itself, and you will see that the rotor condition is in this condition. This condition is called the squirrel cage condition. Another type is one rotor, but this one is very rare to use because they need a supply, external supply from outside. Okay, this is just the animation, okay, where we have the armature winding, and then we have three-phase winding there. We have the rotor itself. So how it operates? So basically, induction motor operate based on the induced voltage generated in the rotor. So basic for the machine to operate, as I mentioned before, it must have two flux source. Okay, we must put this in our mind, in our brain. Okay, in all time, whenever the motor is trying to rotate, they must have two flux source. Okay, but in the case of induction motor, how they generate two flux source? Okay, first let's see we apply a three-phase voltage to the stator. Okay, we apply three-phase voltage to the stator. So when voltage is there, and then three-phase current will flow to the stator. So the current will produce BS. BS is nothing but the magnetic flux of the stator itself, magnetic flux density. Yeah? So the stator flag will run under synchronous condition using this formula. Okay. And then from the stator itself, when the flag from the stator flow to the rotor, okay, and then the rotor flag will play around or will flow directly to the squirrel cage rotor itself. And because of the rotor is slanted, and the rotor is also made from the aluminum bar or iron cast, and both of end of the rotor is we can say that is short circuit with the clamp or with the end wire, not end wire, end case. So we can see that when the flag flow in the rotor itself, so the induced voltage will be generated. Induced voltage will be generated based on the Faraday's law. Okay, Faraday's law mentioned that whenever there is a flag changes, okay, happen, and then with the number of turn of number of the conductor is there, okay, E equal N d flag over dt. So induced voltage will be generated in the rotor itself. Okay, I forgot to put the formula for the induced voltage or EMF, Faraday's law. So now the stator supply the current and flag, and the flag from the stator flow to the rotor, and the rotor is short circuit. When the rotor is short circuit, induced voltage is generated in the rotor. Okay. So when induced voltage is generated in the rotor itself and it is short circuit, so the rotor will create the rotor current. Okay. When the rotor current is generated, and then the rotor will produce the rotor flag. Okay. So now we have two flags is there. Huh? First flag is come from the stator, and second flag is come from the rotor itself. But the issue here is that BR is the rotor flag, rotate at synchronous speed, but rotor turn at slower speed. Because why? Because they take a few minutes or few seconds for the rotor to generate the rotor flux, so that the rotor flag will interact with the stator flag itself, so that the rotation will be happen. The rotor start to rotate itself. Okay. Actually, the topic of induction motor itself is very, very important and very, very how to say, good for us to understand and study on the very basic principle and how it make the rotation itself. Okay, and then finally when the BS and the BR, okay, BS means that the stator flag, BR means that the rotor flag is attached together. Then the torque will be induced based on this formula. The torque will make the rotor to rotate. Okay. Now let us look at another type of motor, that is field excitation synchronous motor. Previously, we have discussed the operation of the DC motor. Okay, and then we have discussed the operation of the induction motor. DC motor is having a two flux source, two flux supply from permanent magnet and also from the winding itself. But in the case of induction motor, we don't have any flux from permanent magnet. We can simply get the flux source from the supply, three-phase or single-phase supply at our home. But the rotor itself is not synchronous. Rotor rotation is not synchronous because it takes some time for the rotor flag to catch the stator flag. So another researcher have developed field excitation synchronous motor. The key point here is they want to make the rotor rotation synchronized with the field stator field, or we can say the synchronous rotation speed. Okay, because we have a speed of the flag, and also the rotor need to be synchronized in the between the rotation and have the same speed itself. For example, if the stator flag rotate in 1200 revolution per minute, so the rotor itself will also operate and run at the same speed. The key idea is that still we need to have a two supply. Okay, first we have a three-phase armature winding, either three-phase or single-phase. Here is okay. So you can see in red, yellow, and blue color is nothing but the armature winding three-phase. Okay. For both cases, we have a three-phase armature winding there. And then in the rotor, okay, where the second flux come from? Okay, first flux come from armature winding. So second flux is come from the external supply to the rotor. Okay, this is rotor, and we have the external supply, and we can see that the rotor has a winding. Rotor has a winding here. Okay, all the rotor has a winding. Okay, and the winding will be given a supply from the external DC supply. Okay, so now we have two source of the flux that is come from the three-phase armature winding, and second flux come from the DC supply itself. So when there is two supply, so the process of the direction and repelling from both of the magnet, okay, will be happen, and then the rotor start to rotate. So we have two type of FE or field excitation synchronous motor. That is salient pole. Salient pole is nothing but we can see that the pole of the rotor is in the salient condition. And also cylindrical pole is nothing but the pole of the rotor is in cylinder condition. Okay. So the idea how it make the synchronous motor rotate, rotor and the rotor rotation is a synchronous speed with the flux rotation or magnetic field rotation, magnetic field speed. So it relies actually between the direction on the stator rotating magnetic field and the rotor DC excited magnetic field. Okay, DC has a constant magnetic field. Actually, we can vary this because we are using DC supply. But at one time, the supply is constant, so we can say it produces a constant magnetic field. So from this figure, okay, we can see that this is the DC supply. So when we give a supply to the rotor itself, okay, so rotor will produce the constant magnetic field, okay, and then we have also second supply that is from the AC supply itself that will produce the magnetic field from the stator or from the AC. So both magnetic field will lock together and then to rotate at the same synchronous speed. So rotor speed at the same speed of the magnetic field from the supply. So once the rotor is brought close to the stator speed, the opposite magnetic poles align and pull each other along. So this is the basic fundamental when they are close together. So different pole will attract and then same pole will repel. So it will cause the rotor to spin in perfect synchronism with the stator field. But the disadvantage of this motor is that it is not self-starting. So what they have to do is that we need to accelerate to the near synchronous speed. Okay, we need to make the rotor to rotate. Okay, we need to rotate the rotor itself until the near synchronous speed, so that after once it reaches the same speed of the synchronous, then the magnetic field from the supply, okay, will attract together and will lock, so that the rotor and the synchronous field will be run in a synchronous mode. Okay, usually they are using a damper winding like a squirrel cage or a small motor to run the rotor at the initial stage. Okay, to avoid the use of field excitation. Okay, in this case we have a DC supply. Okay, field excitation, we have DC supply. To avoid this one, we don't want any supply here, so we simply can use the permanent magnet. Okay, we can change the DC field by using the permanent magnet, and then we can call it permanent magnet synchronous motor. When we look at this figure, okay, as I mentioned before, there are two types of permanent magnet synchronous motor. First is surface mounted. The second is interior permanent magnet. Surface mounted is nothing but the permanent magnet is located at the surface of the rotor. You can see in the brown color, we have 4 brown permanent magnet here that is located on the surface of the rotor. And then for the interior case, okay, it is more similar like the cylindrical pole rotor. Okay, the magnet is located inside or inner of the rotor itself. The same principle is happen. That is the first flux come from the stator itself or from stator winding. Okay, and the second flux come from the permanent magnet itself. So when there are two flux in this machine on this motor, so the process of repelling and attaching will be happen, and the rotor will try to start to rotate. The same goes like the field excitation. To run the permanent magnet synchronous motor, they must use a special damper winding, or they need to run the rotor at the initial until the rotor achieve the synchronous speed, and then it will attract to the magnetic field speed of the flux from the stator, and then only they will run together. Okay, this is just the linear diagram of the permanent magnet synchronous motor. We can see that this is the surface mounted. Okay, upper part is the stator, lower part is the rotor. So this is the magnet. Okay, so the magnet at the surface of the rotor will flow to the direction on the stator, and then it will come back to the rotor itself to make a one loop cycle. So we can see that the polarity of magnet is in how to say, in different polarity. So maybe this one is a north polarity, and this is south polarity, and so on. Okay, in order to generate different type of rotor, okay, researchers have found that very various design of the rotor condition. Okay, so we can see that this is a very normal one, surface mounted. So simply put the magnet on the surface of the rotor. Second one, there is a permanent magnet, but there is a flux barrier there. Flux barrier is nothing but they want to have a low reluctance path, so that the flux will be generated much higher. And then like this one, this is the pole. They put the permanent magnet at the pole of each of the pole of the rotor itself. For the case of interior permanent magnet, okay, they can simply put the permanent magnet at the inner part of the rotor at different design and auto categories. But the key idea, the main thing is that they want to produce the constant magnetic flux, or they want to produce magnetic flux in the rotor itself, so that the flux from the rotor can attract with the flux from the stator, so that the rotor can be rotated. And some other technique, they also studies that is the skew magnetization. The main thing that when compared to the straight magnetization of the magnet, this is for the case of surface permanent magnet. This is normal. Straight magnetization is the normal, but skew magnetization, they make the research, and they found that they can reduce thrust harmonics, they can reduce the clogging torque, noise, vibration, and appropriately skewed PM can optimize motor efficiency and reducing unwanted mechanical stress. In our lab, in the UTSM, we also did some of this experiment and analysis. You can see that when we skew the magnet itself, some of the performance will be reduced, okay, in terms of torque and power, reduce a bit, about maybe 5 to 10%. But the most important thing is that we can reduce all of this, okay, all of this disadvantage. Okay, now we go to the juice of the presentation today. That is the flux switching machine. Okay, so I will go on introduction, and I will explain more detail on permanent magnet, flux switching machine, field excitation, flux switching machine, hybrid excitation, and a bit on comparison between salient versus the segmented stator and rotor. Okay, why suddenly 15 years back? Actually, I did my PhD in Japan I finished in 2012, so I came to Japan in 2009. So at that time, I can see about 16 years back. At that time, when my supervisor asked me, what is the topic that you want to do during your PhD? So I say, oh, I don't have any idea. I come from Malaysia. Malaysia is not a developed country. We don't have my idea is that I know only induction motor only. And then my supervisor gives me a task about 1 month for me to find the latest research and development on electric motor itself. But of course, in 1 month, I couldn't find, and I cannot find the suitable topics. And my supervisor helped me. Okay, you study this one. He gave me one paper, research paper. This paper published in 2007. Okay, just very recent. 2007, I come to Japan. 2009, after 2 years, he said, okay, you explore this one. Instead from that, I learned that the paper that my supervisor gave is nothing but the research on the flux switching machine. So we can say it started from 2007. I just continued from 2009, and now is about 18 years, 18 years of flux switching machine. The motivation is nothing but we need a high torque motor. We need a high torque density motor. We need high efficiency, and we need a robust brushless operation. The idea is that when we want to have a different type of motor, we can have we need to have a two flux sources. Okay, this is very fundamental. So to make a robust brushless operation, we must avoid the use of brush, the use of commutator, and also the DC supply to the rotor itself. Okay, we must make the rotor itself become the single salient pole rotor without any supply or any flux sources. That is the idea. So when researcher developed the flux switching machine, okay, the definition is that FSM is a brushless AC machine where both the armature winding, okay, armature winding is one flux source, and excitation, okay, either come from permanent magnet or field. Okay, this is the second flux source. Okay, are located on the stator. Wow, this is very good to see this one, to hear this one. Okay, so when the armature winding and the excitation PM or field are located in the stator, so the rotor becomes simple. The rotor becomes simple salient iron structure. Okay, so the key idea is the flux linkage in the armature winding switches between the stator tip as the rotor rotates. I will explain this later, how the switches happen. So now we have a basic structure now, okay? From the definition, the stator has armature winding and excitation. So stator include armature winding and excitation or PM. It can be either salient or segmented stator, while the rotor itself have only two steel dimension with no winding, no magnet. Okay, it can be salient and also segmented design. Now I hope you have some idea on how the flux switching machine structure itself. So generally, flux switching machine can be categorized into three parts, three types. Okay, that is based on the flux sources. Okay, first is permanent magnet. Okay, in this case we have only permanent magnet as a main flux source. The second flux is come from the armature itself. So if you look at this figure, the green one, the green is the permanent magnet that is attached on the stator itself. Okay, and the blue is the coil that is winding around the permanent magnet. So this is the armature coil. Okay, now we have two flux sources that is come from stator and also armature winding, and second flux come from the permanent magnet. This will make the rotor. Okay, you can see the rotor is just a simple one piece of rotor, one piece iron of rotor. Okay, but still we have two flux sources. Okay, the second type of flux switching machine is field excitation. Okay, we can just convert the permanent magnet to the field excitation. Okay, DC supply. Okay, DC supply come from outside to the field excitation, and then another supply of flux is come from the armature. Okay, the same case of the previous PM. The armature winding is same. The only difference is that the permanent magnet is changed to the field excitation. Now we have two flux source in the stator itself. And when the two flux source, movement will be happen, attracting and repelling procedure or process will be happen, and rotor can be rotated. Okay, I will explain that later, how the rotor rotates. And then we have the hybrid excitation types. That is the combination of permanent magnet and also the Fe. So we can see from this figure, okay, we have the green one is the permanent magnet itself. Okay, warp around all the stator. And then we have the field excitation. Okay. And when we have the armature, that is in blue color. So we have three flux sources actually in the case of hybrid excitation. First flux source is come from the armature itself. Second flux is from the field excitation, and third flux come from the permanent magnet. And the rotor still in the hollow or salient pole single piece iron. All right, so now let us look at the condition of the permanent magnet FSM. Okay. As we discussed previously, the basic structure of permanent magnet FSM, it has all active parts. Active part means the flux source, such as armature coil and permanent magnet in the stator. And usually for the case of permanent magnet FSM, it use a segmented stator. What is the definition of segmented stator? Is that the stator is separate each other. So you can look from this figure. Okay, this is the permanent magnet. Is sandwiched between the stator. This is the stator. This is the segmented stator. Okay. So permanent magnet, stator, permanent magnet, stator. So stator itself is like a single piece or segmented like this. Okay. In between that is the permanent magnet. Okay. So we can simply design different stator, and then later we will combine together. And then rotor is a tooth steel lamination with no windings or magnets. Okay, this is the rotor itself. There are no winding, no magnet, as previously mentioned. The armature coil located at the stator itself. Okay, this is the armature coil, and wound between segmented rod stator in concentrated winding. Concentrated winding means that the winding is just simple winding like this, side by side winding. Okay, side by side winding is called the concentrated winding. Okay, this is winding, and then this is another winding. Okay, another type of different winding is the distributed winding. This winding is nothing but distributed is that this overlap each other like this. Okay, this is distributed winding. Okay, this is the side by side or concentrated winding. And we have the permanent magnet radial flux, alternate polarity sandwiched between the segmented stator. Okay, polarity of the magnet is like this, and another one is like this direction. So this is called the alternate polarity of the permanent magnet. Okay, this is case of example of 12 slot 10 pole MFSM. All right. So the idea on the operating principle is very simple. Okay, first we have a stator. Okay, inside the stator there is a permanent magnet. Permanent magnet, of course, there is a north pole and a south pole. So the flux from the north pole will go to the south pole. Okay, and the flux go to the south pole, and then it will flow also to the rotor. So flux will make two different flux. First, PM flux path 1. Okay, that will be flow to the stator through AC coil plus to the rotor itself. Second, permanent flux 2, they will go through the AC coil negative, AC coil negative to the rotor itself. And flux from the rotor is combined and make a complete flux pass through the stator, go back to the permanent magnet itself. Okay. So we can see that when the flux pass through the rotor, okay, when the flux from the magnet or from the stator pass to the rotor itself, the rotor become energized. The rotor is now become the magnet. Okay, it's simple like we can say that if we have the iron core here, okay, and then we have supply, we have the supply of the coil here. Okay, this is the coil supply. Okay, so when we give a supply current of this direction, so this coil or the solenoid will generate magnetic field in this direction. Okay, when this magnetic field flow to the coil, okay, so the coil will be energized. The core will be energized with the flux itself in there, so it can become like a magnet, okay? So this will be the north pole of the core, this will be the south pole of the core. So now the core itself will become like a magnet because there is a flux there, okay? So same case like this, okay, the rotor is energized with the flux from the stator. So now the rotor has become a magnet that is producing the flux from north to the south direction. Now we have the flux in the rotor, we have flux in the stator, then the attraction and the repelling process will happen there, and the rotor will start to rotate. Okay. Okay, this is the very detail of the operating principle in the case of permanent magnet flux switching machine. We look at the rectilinear diagram. Okay, in the case of A, we have a stator here. Okay, the upper part is the stator, the lower part is the rotor. Okay, the lower part is the rotor. In the stator, we have only two flux source. That is, first come from permanent magnet. Okay, direction is toward the right side. And then we have the armature. Okay, winding is like this direction. Okay, armature. Okay. Now let's see the pole of the rotor. We have a pole 1 and we have pole 2 here. Okay, from the permanent magnet on the stator, the flux from magnet will flow to the downward direction, okay, to P2. Okay, so P2 receive the flux here, so this will become the south polarity. Okay, this will become the south polarity of P2, and P1 bring the flux from the rotor to the stator to make one complete cycle. So this will be the north polarity of P1. Okay. Okay. When this condition is happen, together with the flux that come from the armature itself. Okay, this is the armature. So we have the flux from the armature coil. So it will react together, and then the rotor will start to move. Okay, the process of pulling and also repelling will be generated. The rotor will start to move. Let's say the rotor move in counterclockwise direction. Okay, CCW counterclockwise direction. Now the P1 will move to the left side, and P2 will also move further to the left side. Okay, so look at the condition B. Now P2 is now happen to be at this location. Mean that P2 is now at the P1 position that is initially there, and then another pole is come from here. We call it P3. Okay. The same direction of flux come from magnet. Okay, we have a magnet here in the stator. Okay, flow to the rotor. Okay, now the P3 become, because P3 receive the flux, so P3 become the south. Okay, and P2 become the north. Okay, that is, that will bring flux from the rotor to the stator itself. So together with the flux that come from the armature itself. Okay, so the flux will be play around there, attracting, repelling, happen, and then it will move the rotor forward again. Okay, but the key here is that first you look at the condition A. Okay, P2 is having a south position. Okay, south pole condition. But after movement to the counterclockwise direction, movement to the left side, now P2 is having a north direction of the flux. So we can say that actually the flux has been switched. Okay, the flux polarity from south has been switched to the north polarity. Okay, from south to north polarity at the same pole P2. Okay, it changed the polarity from south to north. So that's why we call the flux has been switching. When the flux has been switching, then it will continue. Sometimes it becomes south, sometimes it becomes north, and sometimes it becomes south, and we'll repeat this process until we stop the rotor. So that's why they call flux switching machine. Okay, I hope you understand this very simple, very fundamental explanation on the operating principle. Okay, this is the example of the 12 slot 10 pole PM FSM. 12 slot is nothing but we have a slot or armature with the number of 12. Okay, this is the green one is the armature itself. It is 12 slot. 10 pole is nothing but the number of pole of the rotor itself. Okay. Then this is the design variation of the permanent magnet. FSM, they can have a 12 slot 10 pole E core. E core is nothing but we can see that like the letter of E. You can see this is like the E, so they call it E core. And then we have a C core. C core is conventional. C core, C like this, or like this C. Sometimes they call also U core. There also a multi-tooth. Okay, at the tooth of the stator, there is a multi-tooth here. The advantage is just to make the flux to be more concentrated. And they have also PM sandwich. Okay, PM and the stator is sandwiched together to make the flux focus in very, very high density condition. Okay, this is the other design. They have a threshold tempo reduce half PM. Okay, they remove this permanent magnet. Okay, actually, there are 12 permanent magnet in the initial design, but they have reduced to only 6. Okay, only 6. Okay, you can see the black color is permanent magnet. Previously, they have previously they have 12, but now they reduce half of them. Okay, and then there are also 12 slot 14 pole. 14 pole. Also, they reduce half of magnet, and they also reduce part of the stator yoke itself to make the motor become lightweight. And also, there is a modular rotor, PMFSM. Previously, we only see that the rotor is in the salient single piece rotor. This is single piece rotor, this is single piece rotor. But there are also researchers who did the design on the modular rotor. Means that the rotor is also like a stator. It has been segmented. One segment, or two segment, 3, 4, and 5. There is a 5 segment or 5 module. Okay, same like the stator itself. Stator also have a different module. The module 1, 2, and so on. Okay. Okay, once we understand the basic principle of the permanent magnet flux switching machine, the rest will be easy for us to understand. Okay. Nothing but field excitation flux switching machine. So the basic structure is, of course, they must have the armature winding, okay, on the stator, and DC field coil that replace the permanent magnet itself. Okay, but usually for the case of field excitation, they are using a salient rotor. So sorry, salient stator. Salient stator means stator is like the previous rotor, that is single stator itself, without any separated or without any segment. Can see here also single or salient stator, single piece of stator iron is there. Okay, and then for the rotor, it can be either salient or segmented. Still, there is no winding there. And then armature coil, they have a overlap with the DC coil. Okay, overlap means that the armature coil like this. Okay, the blue one is the armature coil A1. So this is the winding of the armature. Okay, the winding of the armature. And then for the DC or FEC, this is the winding of the FEC. So this is actually what we call the overlap winding. Overlap between the FEC and also the armature coil itself. In the case of permanent magnet, there are no overlap. They are concentrated. Okay. And then the DC excitation provide current for flux strengthening and flux weakening. Okay, this is the advantage of DC field coil. We can increase the flux, increase the current to increase the flux, so that we call it flux strengthening. Or we can decrease or give a negative current, so it will be reducing the flux or flux weakening. Okay, this is the example of 8 slot 4 pole FEFSM. Okay, we have 8 slot of total. 4 slot from armature, 4 slot from FEC, and also the 4 pole of the rotor itself. Okay, the same process operating principle from the stator, okay, produce DC flux, and it will produce the flux pass 1 to the AC coil positive, and flux pass 2 to the AC coil negative. So it will generate rotor flux. So rotor will have the north and south polarities there, and then it will complete the flux pass to the stator itself. Okay. And the rectilinear diagram of the operating principle, it is much similar. The only difference is that We have the FEC winding and the armature winding here. So basically the FEC winding is like this. Okay, if you look at this part, FEC winding is like this. So we will have the flux direction toward down of the page. So at this P1 will receive the flux and the polarity will be south. Okay, and then when the different configuration of the FEC winding, okay, like this. So the flux will be generated toward the upper of this line. So P1 is now bring the flux from stator to the rotor, and now it become the north polarity Islam. Same goes to the P2. P2 here receive the flux, so this is the south polarity, and then P2 here bring the flux and become the north polarity. Okay, we can see that the switches from the south and to the north polarity of P2, okay, will create the switching process. That sometimes is become sub polarity, sometimes it become not polarity. So it's always switch from the south to north to south and so on. So that's why they call the flux switching machine. Okay. So this is the case of 18 slot, 10 pole FFSM non-overlap. Non-overlap means that the armature is in the inner part of the stator, while the FEC is located at the outer part of the stator itself. Okay. And then is the design variation of the field excitation FSM. This is actually the design that I did in Japan. This is the design of field excitation fluctuation machine supported by the Toyota company. And we have also inner rotor 9 slot 5 pole and outer rotor 12 slot 7 pole. But this odd number of pole, 5 pole and 7 pole, is very very difficult to apply in real application because of the unbalanced pulling force, because the rotor numbers is not even. So pulling force will be generated throughout all the rotor itself. It will make the noise and the vibration of the motor. Now we go for the last FSM, that is hybrid excitation. So I think you all get a very, very fruitful idea today. Okay, we have a permanent magnet FSM, field excitation FSM. Now the hybrid is the combination of the both permanent magnet and the field excitation. Okay, the same case, there are armature winding, DC field coil, and PM. Okay, and then there is also a single state lamination rotor. It can be salient or segment. Armature coil one outlier stator. And then we have radial flux PM, alternate polarity sandwich between the segment. And last but not least, we have a DC excitation on an inner layer stator, not overlap with armature winding. So from the example, we can see that we have permanent magnet here in the blue part, and then we have this the field winding. Field winding is in the green color inside of the inner stator, and the armature winding is the green yellow part that is outside the outer stator. So in the case of hybrid excitation, we have 3 flux sources actually. That is from the PM, FEC, and also from the armature winding. The process is also similar with the previous case, but for the case of hybrid, so they are having a flux strengthening and weakening condition that can control the permanent magnet flux. So we can see from this flow chart, we can say that the stator consists of PM flux and FEC flux that goes to the rotor. So the rotor combined flux with the armature coil, so the resulting flux will be, if the IDC is more than 0, it will be the flux strengthening. If IDC equal to 0, it is nothing that the flux come from the PM itself, or we can say base PM flux. If IDC is less than 0, negative current, so the condition is nothing but the flux weakening condition. Okay, the operating principle is similar. Just combine the principle of the permanent magnet and the field excitation FSM. So the difference is there. We can see that the first case is field strengthening, where the both flux from PM and FEC combine together here, flow to the rotor P1, okay, and then it will bring back to the stator part, to make one complete cycle. While the field awakening condition, okay, field awakening is nothing but to reduce the flux from the permanent magnet. Okay, so that only flux from PM flow to the P1. Okay, that will bring flux back to the stator itself. If we see flux, we just flow around the stator itself. Okay. Okay, this is the sample of 6-slot 4-pole. And then this is the sample of 12-slot 10-pole. HE-FSM. Okay, various design. You can see that we have a 12-slot 10-pole outer FEC. Outer FEC means FEC is outside. This blue is FEC. Okay. Armature is inside of the inner stator. Non-overlap. Okay. We have E-core, HEFSM. Okay. E-core means like, it is like the capital E, like this, E. Okay. Capital E, yeah. And then segmented stator. Stator is segment, means that stator has a different separate field, separate stator core. Okay. Non-overlap. And then we have 12-slot 10-pole HFSM, salient stator, and non-overlap. Okay, next I just want to give some idea what is actually salient and what is actually segmented. Okay, in case of stator, salient means that the stator itself is built by one piece iron that is stacked together. Okay, single piece iron they stack together to become the stator laminated core. Okay, so this is a conventional design. But for the case of segmented, okay, they are having a different segment. Okay, in this case, we have 4 segments. Okay, and this actually has been applied in Malaysia. They are using it in Ekremo electric scooter. Actually, the company can provide 6 stator segment, but for the EV application, they are only need these 4 4 segment of the stator to produce about 100 Newton meter of torque to run the electric scooter. They can simply add another 1 stator or second stator here to make a complete 6 stator to increase more torque of the electric scooter itself. So actually this is the advantage that we can apply it in the real life application. Okay. This is like the difference between the segmented and the salient in terms of structure. I have explained many times. Stator made of individual 2 segment. Salient case is stator core is continuous limited piece single stator. The winding, in terms of winding, okay, for segmented it will be easy because it will wound on each segment individually, separately before assembly. For salient is difficult because insertion the winding is close to the other slot. In terms of magnetic path, it is very higher magnetic and also higher magnetic latitude between segment, and it is continuous, between that the flux from one stator cannot flow to the other stator. It will flow on the stator itself. In the case of salient, the flux continues flow all around the stator that provide low reluctant path. In terms of flux leakage, slightly high due to air gap between the segment, but for the salient, low flux leakage because it continue flow on the stator itself. But for cooling performance, for segmented, it is better because we can dissipate the heat directly through housing from the segment of the stator. For salient, heat dissipation or cooling performance is moderate because the heat flow in the stator entire core itself. Okay, for the case of rotor, okay, rotor also can have a salient or segmented or modular rotor. So you can see salient rotor is like this, just a single piece of iron. And then segmented rotor can be like this condition. Okay, of course, they need to, if you want to assemble, they need to put some like insulation or ring here, okay, to make it in circular shape, circular design. And here they will put the shaft and so on. And for the case of modular rotor like this, okay, they can also add the insulator or ring here, okay, to make it a complete rotor like this, okay. And the feature, okay, the structure is almost similar like the previous stator. We can see that the structure itself is different, segment is different, and salient is different. Salient is just a simple core. Flux pass, okay, through each separate segment, improving magnetic control when compared to salient. Pass through all stator across the air gap. Torque ripple is low for the case of segment when compared to the salient. And then cooling is better, same like the stator condition also. And higher iron loss of the salient. Application commonly used in flux switching and switch reluctant machine for the case of segmented. For salient is used in traditional synchronous machine and alternators. Okay, I think I'm about to finish my discussion or lecture today, and then I will give some summary and conclusion. What I can summarize from my presentation today is that the difference between the permanent magnet flux switching machine, PMFSM, FEFSM, as well as the HEFSM. So the features of the flux source, PMFSM only permanent magnet, FEFSM only DC, while HEFSM combination of both. In terms of control of air gap flux, it is fixed because depend on the permanent magnet constant flux only. But for FEFSM, it can be controlled because we can control the current field. But for the HFSM, it can partly controllable. Okay, we can make it flux strengthening or flux weakening condition. In terms of excitation loss, no, because there is no field winding. In FFSM, high loss due to the DC field coil, while HFSM moderate loss because there is a bit still using the DC field coil. In terms of efficiency, the best is PMFSM because they are using no copper. They use only permanent magnet. So efficiency is high, no losses of the copper loss. FFSM and the HEFSM has a moderate efficiency when compared to PMFSM. And last but not least, the flux weakening capability is limited because constant flux. But FFSM and HFSM has flux weakening capability because it can control the flux there. So in terms of performance of torque, okay, PMFSM become the highest torque there. FFSM moderate torque, HFSM also high because of a combination of the flux source. The cost for the PMSM is very high because we are using rare earth magnet. Low for FFSM and moderate for hybrid. Temperature sensitivity, okay. In PMSM, there are a high risk of permanent magnet demagnetization. Means that the magnet inside the PMSF will be killed and demagnetized, so it cannot perform. It cannot produce the magnetic flux density as the initial condition. FFSM low, no permanent magnet. FSM is medium, temperature sensitivity. In terms of control, this is very simple. Okay, just only control for the armature current itself. This one is moderate, and for HFSM is more complex. And finally, the typical application is in high performance drive such as EV motors for the PMFSM. FFSM application requiring wide speed range, HFSM can be used in EV, HEV, where efficiency and flexibility are crucial. Okay. Okay, from this chart, we can say that the design and development of the permanent magnet FFSM is about 71% when compared to the FFSM 14% and HEFSM 15%. Why? Okay, we can see why permanent magnet FSM is 71% because it provides high torque and power density. Okay, and it doesn't have any losses from the FEC coil itself. Okay, the use of PM improve efficiency without external excitation. For the case of FEFSM, okay, it is preferred because it can eliminate the rare earth PM and also have cost-effective environmentally sustainable, and also they have a flood control capability via DC excitation. But the only issue is that the torque production and power is very low, much lower when compared to the PMFSM. Even if we optimize the initial design of FAFSM, we cannot achieve the same performance as the PMFSM. And then hybrid station 15%, combined advantage of PMFSM and FAFSM, enabling variable flood control and improve performance under different load conditions. The only thing for the HEFSM is that because of the structure itself, all flood sources are located on the stator itself. So the compact structure of the stator will make it difficult to manufacture. And then the heat issue also in the stator itself is difficult to eliminate or to reduce. So what we can say that in the development trend, okay, PMFSM dominates current research, but FFSM and HFSM are gaining attention due to cost, material sustainability, and controllable flow for future machine. Okay, as a conclusion for my lecture today, I can say that research on FSM, okay, have been more effective during the last decade due to the advantages of robust rotor structure. This is actually the key of the FSM, robust rotor structure. High torque density, especially for PM FSM, and favorable thermal dissipation. Okay, various armature slot. Okay, we can say that 12 slot, 14 slot, 9 slot, and so on. With rotor pole, okay, we have rotor pole number of 10 pole, 14 pole, and so on. And some special structure there we have a magnet, a sandwich in the stator. Okay, that employ different approach to mitigate the drawback of commercial FSM has been highlighted. Okay. Okay, the primary motivation is to identify potential research gap that require more focus in FSM development, particularly for industrial application and as well as transportation. Okay, I think that's all my lecture today. I hope you enjoy my session. I'm sorry to take a longer time to finish this presentation. Thank you very much, Pak Wei.
Terima kasih, Prof. Ini tidak
So we open for Q&A or finish.
harap-harap internet saya bagus ini. Terima kasih, Prof. Lecture pagi ini. Thank you. Kemudian saya tak perlu summary ya, karena sudah ada summary tadi. Terima kasih.
Okay.
Satu hal, kalau ada yang ingin bertanya, audience participant, if you have any question can be posed in chat. Ada yang mau bertanya?
Saya boleh tanya, Pak Wi?
Boleh, silakan.
Daripada nggak ada yang tanya. Mungkin saya bertanya dalam bahasa saja supaya lebih fluent, lebih lancar. Prof. Erwan bisa dengar ya suara saya? Bisa. Di summary tadi, dalam summary, Prof. Erwan menyebutkan bahwa salah satu kekurangan PM FSM adalah field weakening capability, ya, lack of field weakening capability dibandingkan yang lain. Nah, saya ingin tahu apa sebenarnya pengaruh lack of field weakening capability terhadap performance atau mungkin ya penggunaan PMFSM. Apakah field weakening capability itu sesuatu yang memberikan benefit atau tidak? Itu dulu mungkin dari saya, Prof.
Baik. Terima kasih atas soalannya. So basically, when we look at the case of permanent magnet, okay, permanent magnet is having a constant flux, okay. So when we put the armature current itself, armature flux itself, it will directly react with the constant flux of the permanent magnet. So means that if the permanent permanent magnet itself initially has a very high magnetic flux density. Okay, the output of the machine of the motor itself will be at the high condition, very high torque, very high power, and so on.
Yep.
So in order to play around with the less performance, okay, we need to control the flux. We need to reduce the flux.
Oh, I
Okay,
see.
so but the initial stage of the permanent itself, dia sudah punya flux yang constant yang tinggi, Pak.
Iya,
Jadi
iya.
bila flux-nya sudah tinggi, jadi kita susah untuk mengawal flux-nya kalau kita nak guna untuk dalam keadaan yang rendah, dalam keadaan yang torque rendah. Jadi kita
Oke.
perlukan flux weakening atau field weakening. Jadi
I see, I
terjadi
see.
misalnya berbeza dengan keadaan yang hybrid. Okay. Kalau hybrid, kita ada dua sumber flux, kita ada magnet dan juga kita ada DC coil. So, jadi permanent magnet flux itu sudah constant. Jadi kita boleh kurangkannya dengan memberikan negatif DC flux, means that the reverse flux. So reverse flux akan kill the permanent flux. So kita boleh apply dia untuk yang low torque and high speed application. Kalau dalam keadaan initial, high torque, dia hanya boleh operate dalam keadaan yang low speed. Tapi untuk high speed, kita kena kurangkan dia punya flux. So kena kurangkan dia punya torque so that dia boleh run untuk high speed application. Itu saja Pak jawapan dari saya.
Oke, oke. Thank you. Jadi itu mempengaruhi controllability-nya ya.
Ya, ya, benar-benar. Bapak bekerja di bidang kontrol kah? Atau desain?
Pak Wiono lebih tahu. Thank you, Prof.
Ya, ya, ya,
Oke.
ya, welcome. Agak-agak semua faham apa yang saya sampaikan.
Oke, yang kedua, karena efisiensi yang tinggi untuk aplikasi industri seperti apa, Prof? Contohnya.
Oh, okay. Basically kalau untuk FSM ni, flat switching machine, dia sebenarnya kebanyakannya researcher akan buat perbandingan comparison dengan IPMSM. IPMSM adalah interior permanent magnet synchronous motor yang mana dia punya rotor tu, okay, dan rotor tu ada magnet. Okay. Jadi saya sudah tunjukkan tadi di slide-nya, kita ada interior permanent magnet motor, okay, di mana di rotor ada magnet. Kalau dalam kes untuk FSM, di rotor enggak ada apa-apa flux, enggak ada apa-apa sumber flux-nya. Okay, jadi kebanyakan researcher buat perbandingan, termasuk saya pun buat perbandingan dalam research PhD saya untuk perbandingan antara IPMSM yang digunakan dalam HEV Lexus RX450H dalam kenderaan Toyota. So jadi di Toyota tu, Toyota Industry, mereka memang sudah ada IPMSM. Mereka sudah ada motor yang dipakai ataupun Toyota Estima ataupun Toyota Hybrid yang lain pun memang sudah dipakai, sudah digunakan. Jadi saya buat perbandingan FSM, membuat desain yang baru kepada Toyota untuk menghasilkan satu desain yang mempunyai efisiensi yang lebih tinggi daripada IPMSM. Jadi bagaimana untuk menghasilkan efisiensi yang tinggi? Ialah kita kena kurangkan dia punya loss. Itu saja caranya, kan? IPMSM diguna magnet. Tapi kalau saya dalam kes saya guna hybrid excitation. Saya buat sebenarnya tiga-tiga design. Hybrid, buat PM dan juga buat FE. Okay. Jadi performanya sama, cuma efisiensi bagi keadaan yang hybrid adalah tinggi sedikit berbanding dengan IPMSM. So jadi kalau ditanya untuk apa aplikasi di industri, untuk yang design yang saya buat, FSM ni digunakan untuk industri di Toyota untuk hybrid vehicle, untuk Toyota hybrid vehicle. Terima kasih. Itu jawapan saya.
Terima kasih, Prof. Ada yang lain pertanyaannya? Oke, kalau tidak ada, kita tutup untuk session pertama ini.
Oke, insyaAllah. Minggu depan lagi kan, Pak?
Ya, kita berjumpa next Friday at the same time, jam 8 waktu Indonesia dan jam 9 waktu standar Malaysia. Terima
InsyaAllah.
kasih, Prof. Thank you very
Sama-sama.
much.
Thank you very much for all.
Thank
For
you,
your
Prof.
understand, insyaAllah. Okay, welcome. See you next week.
Oke.
Okay, semua. Assalamualaikum semua.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Wah, suaraku kok hilang.